Good morning. We're finishing up Stokes. I'm going to need circulation of the vector field. Over the boundary of triangle cut from x plus y plus z equals 1 by the first octant oriented counterclockwise with view from above. Plus y plus z equals 1. And that's being cut by the first octant, so let's go ahead and put the planes in. Two. So that there's the triangle that we're looking at. View from above, because they say that is how we're going to determine the orientation. Counterclockwise when viewed from above. Change one more thing. So that's the direction we're going. Since we have a positive orientation, we can use Stokes' theorem. Right, so the question is, what surface does that enclose? Encloses the surface of the triangle. We can represent that surface with z equals f of x, y, right? Which is 1 minus x minus y. That's our parameterization. We need a domain. And so we can decide to do either a vertically simple or horizontally simple domain. I'll do vertically simple. X will go 0 to 1, right? Y will go 0 to 1 minus x. Normal vector, negative z sub x, negative z sub y, 1. And that is indeed outward pointing. Let's also find the curl. Partial y, which is 2y, minus partial z. Partial z of the x minus partial x. The z, and then partial x minus partial y. That circulation is this surface integral. That's that flux. Integrating over our domain. Y stays as y, but z is 1 minus x minus y. First component, right? X plus 2y minus 1. 1 minus x minus y, all minus x. And x minus y stays the same. Dotted with dA, 111 dA. Do that dot product. All you're doing is you're adding all the components, right? Because you're just dotting it with 111. What do you get as your dot product? Zero. It requires no work. What's the integral of zero? I asked for one. Circulation of x squared y cubed 1z over the intersection of the cylinder x squared plus y squared equals 4 and the upper hemisphere of x squared plus y squared plus z squared equals 16, oriented counterclockwise when viewed from above. Here it is as viewed from above. this here is our boundary. No, it's not. So that was the sum of it. So that is the boundary. It's oriented counterclockwise. Again, positive orientation. You use Stokes theorem. The question then becomes, what surface is that enclosing? We come over here. It's enclosing that polar cap. Now we just have to parameterize that surface. Since what's being parameterized is the portion of a sphere, we'll start with the parameterization of the sphere. Spheres of radius 4. If you go back, clearly your theta is not being restricted, right? It's going all the way around, it's a complete circle. However, the z is being restricted. Or the phi, rather, right? The phi will go from 0 to whatever angle that is. Now we have to figure out what that angle is. No, that's not hard to do. It's where the two solids intersect, right? X squared plus y squared has to be 4. Replace it in the equation of the sphere. You get 4 plus z squared is 16. That means z squared is 12. But z squared z would be what? Rho cosine of theta? What is the radius at that point? And radius at that point is, oh, no, not 4. It's the radius of the cylinder. You get you get 4 cosine squared of phi is equal to 12. No. It is 4. 16 cosine squared phi is equal to 12. Divide by 16. Cosine squared is 3/4. Cosine phi is root 3/2. Positive because we're dealing with the upper part. So what's phi? Cosine of what angle is root 3/2? Five, 6. X squared plus y squared is 4. Right, that's the cylinder. Z is rho cosine phi. Radius of the sphere is 4. Over 16. 3/4. Take the square root of both sides. Normal vector. Remember, outward pointing normal vector is this. No, it's not. Missing something. Move you down real quick. What's that? 16 sine of phi times that vector. And we still need the curl. Partial y minus partial, okay, so that's 0. 0. 0 minus 3x squared y squared. There's the Stokes theorem statement. Circulation of f dot dr around the boundary of S is just the integral over S of the curl of f dot ds. But then evaluating surface integral, integrating over the domain, evaluate the integrand over our parameterization. Well, that's nice. 0, 0. X is 4 cosine theta sine phi. Y is 4 sine theta sine phi. Oh, you're going to get 16 squared times negative 3. What's 16 squared? Times that by 3. 768. Cosine squared sine squared of phi plus sine squared of phi. It's just sine squared of phi, isn't it? Oh, I'm sorry, it's all multiplication. This dotted with N VA. You do that dot product. It's just going to be a 0 plus 0. Good, that's gone. Now, 768 times 16. What is it? Yes. 12,288. Integrate 2 over, or integrate 0 to pi, integrate 0 pi over 6. Cosine squared. Sine squared, sine to the 5th, cosine phi, d phi, d theta. Oh, good. With respect to phi, it's not too difficult. You're going to get 1/6 sine to the 6th phi, right? What is sine of pi over 6?
The over 2.
1/2, right? Now divide that by 6, 1/12. 12,288 divided by 12. What was it? Should not be 124. $129. Should be 128. So I did something wrong. $10.24. $10.24. Where's that 32 coming from? Oh. Okay, back. It's 1/2 to the 6th power divided by 6, not just a half. Makes it sine to the 6th. So it's 12,288 divided by 6. That counts for that 1/6. Then divide that by 2 to the 6th power. You get 32. Now, the easiest way to do this would probably be to use reduction identity on both sine and cosine. Half times half is a fourth. What's 32 divided by 4? Right, because cosine squared would be a half, 1 plus cosine of 2 theta. Sine squared is a half, 1 minus cosine 2 theta. Two squares. You expand that out, 1 minus cosine squared of 2 theta. and then expand out that cosine squared, not expand, I'm sorry, use reduction identity, a half, 1 minus, or 1 plus cosine of 4 theta. So 1/2 plus a half cosine of 4 theta. One minus a half is a half, right? And then we can factor out the 1/2. What is the period for cosine of 4 theta? That's for cosine. Just regular cosine of theta is 2 pi. What about cosine of 4 theta? You did the wrong operation. 5/2. It's 2 pi divided by 4. We're integrating 0 to 2 pi. Length of that is 2 pi, right? Is that a multiple of pi over 2? Yes, it is. Cosine 4 theta integrates out to 0, and you're just left with 2 pi as your integral. Then multiply that by the minus 4. You get -8. This one is one of those rare occasions where Stokes theorem was actually easier than doing circulation, right? Because you have 3 separate integrals, 3 separate line integrals you have to do. But the way that Stokes theorem was wound up being set up, that wound up being easier. This one, I honestly don't know. Honestly, probably the circulation integral would be the easiest. You should have to determine what's the radius of that circle, so you can parameterize it. And this just felt like a lot of work. But I'll let you be the judge of that, whichever one you want to use. You don't have to use Stokes theorem unless I specifically tell you to. Questions on Stokes? Cool. So those 2 homeworks, Green's theorem, Stokes theorem, both due Thursday. We have one thing left to cover. All that's left is divergence theorem. Next week, we only meet twice. Next Friday is reading and review day, so there's no class. So we only meet Tuesday and Thursday next week. I don't know what I'm going to do about Friday. Whether I'll come in as a student during review, think of it more of extended office hours, or if I'm just gonna say it's a Friday, screw it, I won't stay home. I'll let you know next week what I'm gonna be doing Friday. It's probably gonna be the latter, to be perfectly honest, especially with the Oblivion remaster that dropped. I'll let you know. Divergence theorem on Tuesday. Have a good weekend.